Hey there, engineers. Welcome to Civil Engineering Academy, where we're looking at a problem from reinforced concrete design. And it reads like this: a reinforced concrete column with ties and properties shown will support a 1,300 kip concentric load if the specified longitudinal steel ratio is 0.03. What are most nearly the side dimensions required for the column? And column slenderness effects can be ignored. So here's our column cross section. We're looking for these dimensions here on the sides of the column, and we've got our column properties here. Our F prime sub C is 5,000 psi. Our yield strength of our steel or rebar is 60,000 psi, and then our longitudinal steel ratio that was given in the problem statement. It's 0.03. So let's attack this thing. Now, if you'll recall from your FE reference handbook, there's an equation in there for short columns. So we have short column here, and we know that because the column slenderness effects we can ignore. And so our limits for our main reinforcement are given here. We're supposed to be 0.01, between 0.01 and 0.08. We're right at 0.03, so we meet that criteria. And then our column is tied, even though it's not really shown here that we've got ties around our longitudinal steel here. We are told in the problem statement that we have ties, and if for a tie column, our strength reduction factor, our phi, is 0.65. And then our strength equation, so phi P sub n equals 0.8 times your phi factor, all times 0.85 times F prime sub C times the difference between the gross cross-sectional area of the column minus the area of the steel plus the area of the steel times the yield strength of the steel. So we're going to use this equation right here to solve this thing. So we know that we're getting 1,300 kips for our allowable axial load, right? So all we have to do is set that equal to our strength equation, and we should be able to solve for this thing. Now, first thing I think we want to do is define all the terms, all the A sub ST terms in terms of A sub G, so that we've only got one variable here that we need to solve for. And so the area of our steel, based on this equation here, if we times both sides by AG, the area of our steel equals rho G times AG, right? So if we say the area of our steel equals our rho G times AG, we could say that that equals our 0.03 that we were given times AG. Now, if we substitute in our strength equation here, everywhere that has an A sub ST with a 0.03 AG, I think we will have defined the strength equation in terms of just AG, or the cross-sectional area of the column. And if we solve for that, I think we can get at these dimensions since the column's square. So let's set that up. So if we say our allowable axial force, or 1,300 kips, is going to be equal to 0.8 times our phi factor, which we know from our FE reference manual is 0.65, right, for tied columns. And then all of that is times 0.85 times our F prime sub C. Now, since we're working in kips, we want to keep our units consistent. So we're going to define the strength of the concrete in terms of kips per inch squared, right? And then all of that's going to be times by AG. And then again, we're trying to define every term that's A sub ST in terms of AG, A sub G. And we've defined A sub ST as 0.03 AG. Okay. And then all of that's going to be plus, again, our 0.03 times A sub G, all times our the yield strength of our steel. And again, we're trying to keep things in terms of kips. So we're going to say this one's 60 kips per inch squared. Make sure that's bracketed properly. Okay, so we grind through that, and we should come up with 1,300 kips is going to equal, I won't go through all of the iterations here, but if you grind through all of that, you should end up with 3.07 AG, and your units are kips per inch squared. Bracket that. We divide both sides, right? If we take 1,300 kips and we divide it by 3.07, keeping our units, we're carrying those through. Divide by 3.07 kips per inch squared. We are going to come up with 423.5 inches squared. So that is our AG, or our gross area of the column that's required to resist this allowable axial force. Okay. Well, okay, that gets us the area. So how do we get at what these individual sides will be? Well, obviously this is square, and so we can just take the square root of this number, and we'll get in inches what that side should be. And if we do that, we should come up with 20.6 inches, which is approximately 21 inches, which is our answer B. Okay, hopefully that helps you out. And we will see you on the next one.